Now, whenever you're asked to write a program to solve the problems, it's very important to bear in mind that, now that you're taking discrete math and after you take this course, okay, you don't just write a problem. You don't just write a program for a problem and then walk off and have a cup of coffee and tea and say, look, I'm done. No, that's not sufficient. Okay? It's necessary to also be able to demonstrate to someone else that, look, I wrote a program and I can demonstrate to you, I can prove to you that it works. Okay? And if you don't think it's a very important task to be able to prove to you that it works, just go and have a look at the Therac 25 on Wikipedia. This, machine that's supposed to give radiation therapy. And the sort of like within the first few lines in Wikipedia, you'll see something to the effect of, and due to some concurrent software programming bugs, the Therac 25 occasionally gave high doses of radiation to the patients. High doses, 100 times too much, 1,000 times too much, occasionally resulting in death. Oh, blah, 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 blah. Okay. So, there's no forgiveness for that. Not when you're writing a program. There's no reason why a program should not work properly, correctly, all the time. There's no reason for it, especially no reason for it if you are well versed in the study of discrete math and you appreciate that it is necessary to demonstrate that your program works and you do it. Okay? Because other people rely on these programs. It's in some sense our moral duty when we write a program that solves some problem to ensure that it works correctly all the time. Okay? Correctly all the time. Okay, so now let's go back to the talking head mode. I want to sort of continue that theme of how important it is to be rigorous when you program. You're not just programming to do stuff, okay? And then I want to give you a tip from George Polya, who's a great mathematician. And if great people who I'm going to invoke quotes from say things, then odds are that us lesser people should follow. Okay. Okay, so welcome back to the talking head mode, where we've just finished talking about some applications of discrete math, and when we get more into discrete math and then the theory of computing, we'll ask very deep questions. So just like we ask questions with virus spreading and speed dating and online advertising, we'll ask deep questions about computing. What can we compute? What can we not compute? How quickly can we compute the things we can compute, and so on and so forth. And you can think about these deep questions in the context of the two sort of programming assignment problems that I gave you. Okay. Now, let's sort of take a diversion. And I also mentioned that it is the responsibility of a programmer to not only make sure that their program works for the benefit of other people who are going to use it, traffic schedulers, fuel injection systems, radiation therapy machines, and so on and so forth. But it's also necessary to demonstrate that your program works. Now, I'm not the first person to say this, so here I'm going to quote from a very famous computer science personality, and the first quote that I'm gonna literally just read out is, "Too few people recognize that this high technology so celebrated today is essentially a mathematical technology." Okay, now yes, we build a computer, it's hardware, it's got plastic, it's got a semiconductor chip and this and that and wires. Okay, yes, that's just the object itself. But its inner workings, it's essentially a mathematical device. Okay? And we will build a very accurate and complete, in some sense, model of that computer when we come to answer what can we compute and what can we not compute. Okay, so it's a mathematical device. And what's a program? A program is implementing an algorithm, a sequence of steps that occur one by one. Okay, and that is in some sense a mathematical object, an algorithm. Okay, so a computer is essentially, this high technology is a mathematical device, and when we solve problems with this mathematical device, you know, we're essentially performing a mathematical task. We're writing a program to solve a problem. Okay, and when you write, so what does this guy say? He says, this is Dijkstra, a famous computer scientist who has, algorithms named after him. Okay, what does he say? He says that when you program something, you must demonstrate that your program works. You must demonstrate that it has the required properties. And if you only think about this at the very end, let me just program it now and then I'll prove it later that it works, or I'll leave it to someone else to prove. If that's the way you approach this, then it's never going to happen. Because the only way in which you'll be able to demonstrate that your program works is if, while you're implementing, while you're programming, you have it in mind that you're going to have to prove that it works. And so you program in such a way that it's going to be easy to prove that your program works. For example, you'll program in a modular way with what are called preconditions and what are called postconditions. And it's only when you program in this very rigorous way that you'll be able to prove that your program works, that you'll be able to satisfy this obligation. It's not a desire. It's an obligation of a programmer to show that their program works, to demonstrate it. Okay? And, how do we demonstrate that a program works? Well, that's another interesting side of discrete math. So what I just showed you is that, we use discrete math in order to formulate, to model, and then solve real-world problems. But then, once we solve the real-world problems, we program it. And now we need to demonstrate that the program works. And the reasoning that you need to demonstrate that a program works is pretty formal. So here comes discrete math again. So not only do you need to know discrete math to solve a problem and then program it in as an algorithm, but then you also need to know discrete math in order to prove that your program works. So there's discrete math everywhere. Okay. Now, he goes on to say that, as long as people don't take this view of programming, okay, that it's a mathematical task, and when you write a program, for example, a module for a program, you must have explicit preconditions and postconditions and prove that if your input satisfies the preconditions, then your output satisfies the postconditions, and so on and so forth. If you don't take this approach, we have a software crisis. We will continue to put out software that, like the Therac 25, will, really? We put out an excessive dose of radium? Well, I didn't know that it was going to do that. Otherwise, of course, I wouldn't have given it to the patient. Well, you didn't know it's going to do that because whoever implemented that system didn't demonstrate that it was safe. Demonstrate without any doubt that it was safe. And the only way that we know to demonstrate things without any doubt is through the concept of proof. Okay. And Dijkstra goes on to say that, as long as we have this software crisis, you're going to get quacks and charlatans coming in with all kinds of, weird therapies and this and that, and sometimes they call themselves software engineering gurus. Watch out for the software engineering guru who is not going to demonstrate the validity of his solution. Okay. So that's just to show you that very many famous people, and I'll tell you, this guy was a mathematician and this guy was a fantastic programmer. And even if he doesn't know anything about my problem, I'll have this guy program it for me because I know this guy will ensure that whatever he puts out works. So I hope that, in your career, whatever you put out, you must make sure it works. It's a mathematical adventure to write a program and make sure that it works. Okay, now, since we're talking about discrete math is hard. I've already told you, you cannot be a spectator in discrete math. It's not a spectator sport. You must get down and dirty into the weeds. In discrete math, if you're missing anything, you're missing everything. So you're reading and you're confused about something. Figure it out. Come to me. Figure it out. Go to the TA. Figure it out. Okay? Because that's the nature of math. Okay? And sometimes when you're faced with a problem, you have to be patient. You have to try things. You have to vary the things you try. Okay? And here's a quote from George Polya, a great mathematician. Okay? Think of a mouse who's in an old-fashioned cage with bars. Okay, and after many futile attempts, banging, bouncing, thumping his body against the bars in the cage, try this, try that, try this, try that, hammering my shoulder, hammering my leg, and then finally I find a small opening. The bars are slightly wider apart. Okay, but nevertheless, they're wide enough for me to go through, and now I'm bruised, I'm battered, but I escape through this small opening, and I find freedom. Okay. Now that's what a math problem, or in general any kind of problem, can do. They can enclose you in a cage. You feel lost. Okay. So you have to try things. We call that tinkering. You have to get down and dirty. You can't just look at a problem and say, oh, that's hard, and then hope that, some magical solution will come to you. And if it doesn't, throw your hands up in the air and walk off. No, that's not the way we do math. The way we do math, even when we're reading math, you have a pencil and you're working out things and making sure you understand everything. Then when you have a problem, you sit down, you focus, okay? You're patient, you persevere, you try this, you try that. I mean, imagine if Christopher Columbus came halfway across the ocean and said, oh man, this is a tough trek I've got, I'm going to turn around, okay? You've got to persevere, okay? And so I'm going to show you a problem here. It's a very simple problem. It's not hard to understand, but it emphasizes the need to persevere. So you have got, a box in which there are 6 tiles, 2 of each color. So blue, red, and green. Okay, and the idea is you can connect these tiles of the same color with wires. The wires can, bend and so on and so forth. So the goal is to connect the same color tiles with wires. The wire cannot leave the box, cannot enter tiles except for the 2 tiles that it's connecting, and they cannot cross. And then the question is, can it be done? Can you figure out a way to connect the wires? Okay, now I would say just sit and think about this problem. Try this, try that. First consider the situation. Is it possible? Try this, try that. Maybe you fail. Is it not possible? Try to see if you can convince yourself that it's not possible. Try both conclusions. Don't give up, persevere. Sit tight and wait for a good idea. Okay? And after some time, hopefully you will see one of the solutions. Okay? If not, afterwards you can look at the solution online, okay, in the solution manual. Okay? But this is just, and show this problem to anyone, your best mathematician friend. They'll have to think about it. They'll try this, they'll try that. So you see, this is the way math is. Okay? Anybody has to sit and think about something. It's not obvious, and you can't just give up you can't just give up the whole plot because you don't see the answer immediately. Tinker, try. Okay? Get into the weeds. Okay, so let me summarize by showing you the workflow of a typical discrete math guy. And we saw that in some sense in the problems we discussed. A typical discrete math guy, approaching a problem. The first thing you do is model it. For example, in the virus game, we said that people are squares on a grid, and if 2 of your neighbors are infected, you get infected. So you model the problem. Okay. Now you might think, after modeling the problem, let me solve it. No, you don't solve it. You first go and tinker with easy cases and see if you can understand what's going on. We did exactly that with the virus. Okay, we said, okay, so here are 6 infections. Let's see what happens. In doing that, we sort of build a familiarity with what's going on. We might start seeing things that we can claim. For example, in that example, not everyone gets infected. Okay, and we might ask questions like, how many people are needed to be infected at the beginning to infect everyone? So based on this tinkering with easy cases, now you can sort of build an understanding of the problem. You can now start asking questions, and these questions usually turn into what are called conjectures. So for example, in the virus spreading example, what's the minimum number of infections needed to infect that 7 by 7 grid? And then I conjectured that it was 7. Okay, and now I need to prove that. I need to prove my conjecture. Okay, and when I've proved it, I now know something new that I can go and tell the epidemiologist. Look, for that model of virus spreading you gave me in this population of 550,000 people, only 33% get infected. Okay, or you need at least 8% to infect everyone. These are interesting now theorems that you can prove. Okay, but the first step, the tinkering step, is what I want to focus on. Tinker, 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 because usually, that's what differentiates the professional from the amateur. The amateur writes down the same model as the professional and looks at it. I don't see what to do. Okay. The professional writes down the same model but does not look at it and say, I don't see what to do. Says, you know what, let me take a simple case and see what's going on. Okay, from the simple case, maybe a slightly more complex case. Okay, and now you kind of build a pattern. You see a pattern and you say, oh, I see that this pattern is occurring. Oh, then I'll conjecture that pattern and then I'll prove it. Okay, that's the expert. The amateur writes down the model, stares at it, stares at it, stares at it, stares at it, stares at it. No immediate answer popping into the head, no immediate question popping into the head, walks off and goes for a swim. Okay. All right, and I want to end by putting my money where my mouth is. Okay, so $10 challenge problem. Construct for me a math cartoon. It has to be your own. Okay, and I'll take all those that I get, and the best one I will give the $10 prize to. And of course, if you submit one, I can put it on this website. Okay. Challenge problem number 2 is exactly the subset sum problem. Okay, but instead of that small list with 7 numbers, I have on the website, a gigantic list of 100 numbers. Okay, and these numbers are big numbers. Okay, 27-digit numbers. And so your task is, for this subset, can you find 2 distinct collections of numbers that match? I.e., when you add up the numbers in your 2 sets, they match. Okay, so that's the $100 prize. I'm optimistic. In fact, I hope that someone wins this $100 prize. It's well within your reach. Okay, but now comes the $1,000 prize. Now comes the $1,000 prize. Now the $1,000 prize, you've got to think, this guy Malik, he's no dodo. He's not going to just give away $1,000 like that. So he's probably protected himself somehow. So you can assume that this problem is not trivial. Okay? And I wouldn't even touch this problem unless you got a good handle on the $100 prize. So the $1,000 prize is the domino problem. Okay? But not for this specific set of dominoes, but to write the actual program. So that's the difference between the subset sum problem and the domino problem. In the subset sum problem, I give you a specific set and I ask you, can you find 2 matching subsets? In the domino problem, you have to write a program that can take as input the set of dominoes, just like we discussed, and the output is yes or no. Okay? The output is yes if I can get a sequence of dominoes for which the top and bottom string match, and the output is and then you of course can show me the sequence, and the output should be no if it's not possible. Not possible doesn't mean I didn't find it. Not possible means nobody can find it. Not possible. Okay. And of course, when you write a program, please don't come to me with a program that can infinitely loop. I'm not interested in those kinds of programs. Okay. So there you have it, and I'll see you next lecture.